Brillouin zone. The left face and the right face can be wrapped together, and the top and the bottom can be wrapped together, and the front and back can be wrapped together. And that makes a mathematical object called the 3 torus. And here I just wrote 3 torus because I have no idea how to draw a 3 torus on a 2-dimensional screen. But anyway, you imagine what that is. That's the mathematics. So the Brillouin zone in a 2-dimensional crystal is the 2 torus. This is the 3 torus. And as I said last time, the fact that these are closed manifolds gives you a hint that topology may play a role, because very often topology is based on a theory of closed manifolds. For example, can you wrap things around the waist like this, etc. Now, coming to topological materials. What I'm showing you here, this is just kind of randomly taken out of the literature, but I took this because it's kind of a nice illustration. This is some first principles band structure calculations on 2 materials. These have strong spin-orbit coupling, and that's as I may talk later, usually an ingredient in topological insulators. And the gray dotted curves that are a little hard to see are the calculation without spin orbit, and the red curves are with spin orbit, and these are 2 different materials in the same family. So there are 4 band structures here, and they look kind of similar. All 4 of them are insulators. But I'm going to tell you that the 2 red band structures are topologically equivalent to each other, and the 2 gray band structures are topologically equivalent, but those 2 are inequivalent with each other. So there are 2 classes that these band structures fall into. The red ones fall into one class, and the gray ones fall into the other class. And what do I mean by this? Basically what I mean is, if they're in the same class, it's the case that I can gradually transform this red band structure into that red band structure by gradually changing the Hamiltonian over some kind of path in Hamiltonian space along which the gap never closes. And it turns out that in order to go from this red to this gray band structure, it's not possible to take the red Hamiltonian. You can gradually transform it into the Hamiltonian of the gray Hamiltonian, but in the process of doing that, somewhere along the path, there's a gap closure at one of these points. It closes and opens again. Okay, so this is the basic way in which we decompose different electronic structures into different topological classes. They belong to the same class if it's possible to find a path in Hamiltonian space from A to B along which the gap never closes. This is similar to the topology of closed 2-dimensional manifolds in terms of curvatures that you might know about. You know that you have genus 0, genus 1, genus 2 things. The coffee cup and the donut are famously both of genus 1, so they're topologically equivalent. And then you have higher order 2, 3, etc. And so the definition of topology here is that the coffee cup and the donut are said to be in the same topological class if you can take one along some path of gradual change to the other in such a way that you never do violence by cutting, pinching, poking holes, closing up holes, etc. And the corresponding story in the band structure is that band structure red and band structure gray are equivalent topologically if and only if you can find a path in Hamiltonian space in which you don't do any violence. This time it doesn't have to do with poking holes. It has to do with gap closure and reopening of the electronic band structure. So that's the basic framework. And there's an amazing further analogy between these 2 things, which I have to develop a little more math before I get to, but I'll give you the preview. You probably know that the topological index, well, there are 2 ways of writing the topological index. One is the number of holes, that's called the genus. The Euler characteristic is twice 1 minus the genus, that's this pi. And it turns out that 2 pi times the Euler characteristic is equal to the Gaussian curvature integrated over the surface. You know, the Gaussian curvature, you measure the curvature in two directions and take the product, that's the geometrical curvature. And so that's positive on a sphere, you integrate it, you get 2 pi, here you get 0, here you get minus 2 pi, etc. And so the integral of the Gaussian curvature over this topological surface is equal to the Euler characteristic, and that's true even as you deform the surface until you pinch or cut and reconnect the thing, then the Euler characteristic can jump by an integer. And there's a corresponding statement that we can make about two-dimensional insulators. In this case, we have a two-dimensional Brillouin zone. This Brillouin zone has the topology of a torus. The fact that this torus has a genus of 1 is irrelevant here. I'm not going to be referring anything to do with the inherent geometric curvature of this object, which it doesn't really have because it's just a mathematical construct. But we have a block function of some band. Let's say the first band of an insulator. The block function is defined everywhere on this manifold. And we're going to define something called a Berry curvature that has the property that if I integrate this Berry curvature over the closed manifold, I get 2 pi times an integer, and that integer is called the Chern number. And so we'll get to that in a few minutes, but basically I wanted to set up this analogy between geometrical curvature. This is just intrinsic of a space as it's embedded in a higher dimensional space. Here we ignore the embedding in the higher dimensional space, but we have a new ingredient. We have a complex wave function defined smoothly everywhere on the manifold. And then there's a mathematical theorem that says that the Berry curvature tells you what the Chern index is, which is the topological classification of mappings of complex vectors onto the torus. Okay, so in order to get there, I need to go back and say a little bit more about Berry phases and then introduce Berry curvatures, which I didn't talk about last time. Let me redo the Berry phase, but in a slightly different perspective this time. Last time I went directly to the continuum representation. I think this is actually a little bit more pedagogical. So what we're doing here is starting with the discrete representation. So we have 1, 2, 3, 4, 5, 6, 7 wave functions, or complex vectors in some complex vector space, but I'll think of these as the ground states of some wave functions, or maybe they're block states of different wave vectors. I label them u1, u2, up to un minus 1. And then I construct this object. The phi is minus the imaginary log. So imaginary log is just, it's the phase angle of this object as a complex number. And what I do is I take the inner product of u1 with u2, and then u2 with u3, and keep going until I get un minus 1 times un. So I take the product of inner products of all these wave functions as I go around the loop, and I call that thing phi. Now, as I told you last time, there's a kind of a gauge freedom, and here the gauge freedom is easier to discuss because you just have a discrete model. So suppose I take this wave function and I change its phase by some phase beta. Beta might be pi over 7, right? So I change the phase of this wave function. That shouldn't affect any physical result. And does it affect this phi? Well, of course, no, because U2 appears once as a bra and once as a ket. And when it appears as a ket, it has this phase, but as a bra, it has e to the minus I beta, and those cancel out. And so this gauge twist, or any set of gauge twists on all of these wave functions, has no effect on this overall object here, which is the Berry phase. And so if I now take the density of these points to become denser and denser, and then I take the limit that the density goes to infinity, it's a few lines of algebra to show that you get back the formula for the Berry phase that I wrote this time. These things are sort of like finite difference measures of how the phase is changing as I go around the loop. This thing is the continuum derivative as I go around the loop. But these two things are completely equivalent in the limit that the density of points goes to infinity. Okay, so then there's Berry curvature. So Berry curvature is simply Berry phase per unit area. So here I imagine that I have some wave functions so here I was imagining that they depend upon one parameter lambda. Here I imagine that they depend upon 2 parameters lambda. This could be kx and ky in an insulator. Could be that I have a molecule and lambda x is the displacement of this oxygen atom in the molecule, and lambda y is the displacement of this manganese ion in the molecule, or something. And I look at the ground state as I go around some loop in this two-dimensional parameter space. And what I can do is I can divide this into little plaquettes, And for each little plaquette, I can define the Berry curvature as the Berry phase to go around the little plaquette, which is almost 0 because the plaquette is small. And then I divide it by the area of the plaquette, which is also small. And that gives me a well-defined object, which we call Berry curvature, in the limit that the area goes to 0. And so there's a kind of a Stokes theorem that says that if I want to know the total Berry phase as I integrate around the perimeter, of course that's the sum of the Berry phases of all of the little, all of the little plaquettes. That's just Stokes theorem, and that's what's written here. The Berry phase to go around the perimeter is the integral of the Berry curvature over the surface. And incidentally, if you work out mathematically what the Berry curvature looks like, it has this kind of cute form. What we had for the Berry phase was only one derivative because it really only involved one parameter. So we have the bra times the lambda derivative of the ket. But now we have the lambda derivative of the bra and the lambda derivative of the ket multiplied into each other. So I don't have time to explain exactly where this formula comes from. But you can take my word. For it. Okay, so that's the basic idea of Berry curvature. And here's the statement now about the Chern theorem that I mentioned a little while ago. I claimed that the integral of the Berry curvature over a closed surface has to be 2 pi times integer. And actually, I can prove this to you based on what we've already done. So we imagine, okay, so it has to be some closed surface. Just for this illustration, it's easier to do it for a sphere than for a torus, but the proof goes through for a torus in the same way. You imagine dividing this surface up into 2 regions, region A and region B. And so first I apply Stokes theorem to region A, that's this purple region. And it says that the Berry phase as I go around this boundary is equal to the integral of the Berry curvature around over this patch. Maybe I should have said something back here already that it's going to be important. I said that the Berry phase is really only well-defined modulo 2 pi. And so the fact is that if you know what the wave functions look like on the loop, but you have no knowledge about what's inside, you can calculate the Berry phase using this formula, but it only tells you what the result is as a phase angle modulo 2 pi. In other words, what's really true is that e to the I this is e to the I right-hand side. But of course, this right-hand side is perfectly well defined, so there is, if you have a knowledge of the interior, there is a well-defined value. Okay, so the story here is, for this purple region, this Berry phase is equal to this modulo 2 pi. And then I do the similar thing for the region B. I applied Stokes theorem to region B, and I get that the Berry phase, as I go around this loop, is equal to the integral over the region B. Why is there a minus sign here? Because I have to use a right-hand rule, and when I use the right-hand rule on region B, then I'm traversing this boundary in the opposite direction, and when I traverse it in the opposite direction, I have to introduce a minus sign. Okay, then I add, well, I guess I subtract. I subtract equation B from equation A. The left-hand side is 0. The right-hand side is the sum of the integrals over the 2 regions, so that's the integral over the whole manifold. The right-hand side was only well-defined modulo 2 pi, so I get that this is 0 modulo 2 pi, or another way of saying the same thing is this is equal to 2 pi times an integer, and that integer is called the Chern number. Okay, so I'm sure this went a little fast, and there's not going to be a quiz on this, but I just wanted to show you that the mathematics is intrinsically not so obscure that we can't do it in a few slides, although, of course, I know it's going a little quickly. Let me just mention the example that I did mention last time, which is about the ground state of a spinner in the presence of a magnetic field, where the orientation of the magnetic field is a 2-dimensional parameter space of interest. And so what I told you last time is that if I go around a loop in a magnetic field orientation space, that the Berry phase around the loop is the solid angle divided by 2. And so what that means is that the Berry curvature, which is the Berry phase per solid angle, is half. And actually, because there's no physically special direction on the unit sphere, it means that the Berry phase is a half everywhere on the unit sphere as a measure of Berry phase per solid angle. And so if I integrate that value of 1/2, so Berry curvature is 1/2, integrated over solid angle, divide by 2 pi, I get 1. So it says that the Chern number on the Bloch, this is called the Bloch sphere, if you know that phrase. The Chern number on the Bloch sphere is 1. And this is related to the fact that when you write a representation for spinors, you can never do it in a way which is continuous everywhere on the unit sphere. We usually make a choice which is nice and smooth and well-defined for upspin, but when you get to downspin, there's this funny phase factor that makes it look discontinuous. It's related to the fact that the Bloch sphere has a non-zero Chern number. By the way, this is for spin 1/2. If you do this for spin 1, you get that the curvature is 1 and the Chern number is 2, and so on. And so if you turn it around and say, mathematically, I know from Chern's theorem that the Chern number has to be an insulator, and the Chern number on the unit sphere, well, the unit sphere has 4 pi solid angle, so that means that the only allowed values of spin are multiples of 1/2. I can have 1/2, 1, 3/2, 2, but I can't have spin 2/3, right? So this is kind of amazingly a strong mathematical hint, if you knew nothing else, that angular momentum in quantum mechanics should allow half-integer representations as well as integer representations, but not, 1/3 integer representations and so on. Okay, so maybe that's why we have fermions as well as bosons. Okay, so I've been talking in generality. Everything I said was true in any two-parameter space. For example, it could be structural coordinates in a molecule. But let's consider now the case where the two parameters are the wave vector indices kx and ky of a two-dimensional insulator, which basically lives on a torus. And I want to ask, what is the physical meaning of the Berry phases and the Berry curvature in these two-dimensional systems? So for a two-dimensional insulator, what I told you last time is that the polarization is related to the Berry phases. And more precisely, if I want to know the component of the electric polarization in the y direction, what I should do is, I have to integrate over the Brillouin zone in the x direction and average over that. But for each value of kx, what I want to do is calculate the Berry phase as I go across the Brillouin zone in the y direction. Those Berry phases are plotted here as these blue dots. And then I do an average, and that average tells me the electronic contribution to the polarization along the y direction. So that's the physical meaning of the Berry phases. I can also do Berry phases in the x direction, and those will tell me about the electric polarization in the x direction. I can also do funny little Berry phases around loops. Usually that doesn't mean too much. Okay, maybe I skip that comment. So that's about Berry phases. What about Berry curvatures? So we also can define the Berry curvature on this region. And here's a case where there is a meaningful physical interpretation of the Berry phase. It turns out that in a ferromagnetic metal, so I'm imagining I have a two-dimensional system, it's metallic, I have to have broken time reversal symmetry to get this interesting thing that I'm coming to. So it's a ferromagnetic metallic film. Because it's ferromagnetic, there's a Fermi surface, or a Fermi loop, since we're only in 2 dimensions, a Fermi edge, I don't know what to call it. There's a Berry phase, which is, I call it sigma z because it's the xy component. I probably should have just dropped the z because I really only have 2 dimensions. But anyway, there's a Berry curvature on this region that I can define. And if I integrate the Berry curvature over the occupied Fermi C and divide by 2 pi and multiply by e squared over h, amazingly, that thing is the anomalous Hall conductivity, or more precisely, it's the intrinsic part of the anomalous Hall conductivity. So as I think we heard in previous days, for the anomalous Hall conductivity and the anomalous and the spin Hall conductivity, there are also defect-related mechanisms. There's side jump and skew scattering. But then in addition, there's this intrinsic pure band structure piece. And actually, the history of this is interesting because early on it was quite controversial whether this piece was real or not, because people had the feeling that since it's not coming from scattering, how can it be a transport property? Okay, so I'll come back and, well, at least I'll explain why there's such a connection in the case of an insulator in a moment, which maybe will help you understand that this is the case for a metal. This can be derived using transport theory in a way that I'm not going to do here, but the part of the story I want here is to go to an insulator. So what I want to do is I want to imagine that I increase the Fermi level somehow, so I fill more and more and more of this two-dimensional Brillouin zone until eventually the whole Brillouin zone is occupied. And at that point, and I suppose that there's a gap to the next band, so at that point the system is again an insulator. But I have this filled band in an insulator, and I can integrate the very curvature over this two-dimensional filled band, so I integrate over the entire Brillouin zone, and that gives a contribution to the anomalous hole conductivity that comes from that Brillouin zone. But I told you that if you integrate the very curvature over any closed manifold, and this is a 2 torus, so it's a closed manifold, it has to be 2 pi times the Chern number, and that means that the anomalous hole conductivity of any two-dimensional insulator can either be 0 or it can be e squared over h times some integer, and that if that integer is non-zero, usually it's 1 or minus 1, then we call this the quantum anomalous hole insulator. And you know, for the rest of my talk, and you've already seen it, QAH always means quantum anomalous hole. And sometimes this is also called a Chern insulator. So Chern insulator and quantum anomalous hole insulator are synonyms for one another. So yeah, maybe I mean, if there are immediate questions, but I'm going to come back and explain some of this in more detail. So are there any questions so far? Yeah.
So I might have missed it, but is there a difference between you integrating over the Brillouin zone there and you integrating over the Fermi C in your previous?
No. So, I mean, the only difference is that one is a complete space and one is not. Right? So the Fermi C is not a closed manifold. It's an open, it has a boundary. And the Chern theorem doesn't tell you what this is. And so if this is a ferromagnetic metal, you'll get some result, and it might be 0.273 times e squared over h. Obviously, if you let this shrink to 0, then you're integrating over nothing, and you have to get an integer named 0. The surprising thing is when you let this expand and fill the entire Brillouin zone, you also get an integer, but it doesn't have to be 0. It might be 1 or minus 2 or something else, and that's the Chern number.
So is it basically saying that it's the occupied states that you're integrating?
Yeah.
Of the occupied states?
Yeah, of course, what I really have to do is I have to repeat the calculation for each of the occupied bands. So maybe this insulator has 6 occupied bands, and then there's a gap in there. So really, I have to add, I have to sum over, I mean, I'm kind of sweeping under the rug these kinds of details that I have to sum over all of the occupied bands to get the total Chern number of the physical material that will determine the physical quantum anomalous hole conductivity.
But then you sum all the Chern numbers?
Yeah, you sum all the Chern numbers to get the total Chern numbers of the occupied bands.
It's always an integer, right?
And it's always an integer because if you add
It's not
integers,
like
you
it's
get an
always
integer.
kind of an integer.
Yeah, sure. That if each thing you add up is an integer, then the total is also an integer.
If the bands are fully filled.
Yeah.
Yeah.
Yeah. And there's, you know, as you probably know, there's such a thing as the fractional quantum Hall state. There is also a fractional quantum anomalous Hall state. So there's a subtlety. I'm assuming here that the quantum mechanics is described in a single particle picture in such a way that you have a well-defined block state as a function of wave vector, and then essentially the wave function of the whole system is like a Slater determinant of all of those things. When you go to highly correlated systems, that's not really true anymore. And so when you go to highly correlated systems like fractional quantum Hall effect, it's possible to get you know, fractions like e squared over 3h. But that's just a comment that I'm going to throw out there. For the rest of my talk, I'm talking about systems that are well described at the single particle level. That is to say, the Hamiltonian is essentially a non-interacting mean field Hamiltonian. Yeah.
In the beginning, you discussed the importance of changing Hamiltonians and avoiding
Gap closing. Yeah.
Do you mean the gap closing at each point in K-space or the overall gap closing?
I mean that there can't be anywhere in K-space there can't be a gap closing and opening again. Now, what, of course, so of course, it's very possible to have an insulator where the top valence band looks like this and the lowest conduction band looks like this, and there's an indirect overlap. But everywhere in the Brillouin zone, there's a direct gap. So in that case, mathematically, you can just study the lower manifold of bands, and you can define, these Chern numbers and do everything for those lower bands. And that manifold of lower bands, we say, is topologically equivalent to another one if there's never any gap closure along the path anywhere in the Brillouin zone. But some of those systems are physically metallic, and so this, this mathematics doesn't apply if the system is physically metallic because of indirect overlap. But the topology really applies to the manifold. Let's say that you have an insulator. You have a system that, if it's an insulator, would have 10 electrons per unit cell. That means there should be 10 occupied bands. So I take the first 10 bands, and I ask, is there ever a touching between bands 10 and 11? And if so, then this manifold of 10 bands is not topologically equivalent to another manifold of 10 bands. Yeah?
Your phase duration has to be solution of the Hamiltonian or any differential equation?
Well, the statements that I've been making about all these wave functions really only depend upon the wave functions. Now, usually I'm assuming that these wave functions are the ground states of some Hamiltonian, but the fact is that the properties that I've been writing down, like the electric polarization, the Berry curvature, the anomalous Hall conductivity, are quantities that only depend upon the wave functions themselves directly, and you don't have to know about the Hamiltonian that gave rise to them. And so we sometimes call these geometric quantities for reasons that maybe are a little obscure to you. But in any case, the idea is it just so happens that for these quantities, you don't need to know the underlying Hamiltonian. There's some other things, like we have a theory of orbital magnetization, which has some analogs to the theory of polarization, in some ways the same, in some ways different. One way in which it is different is that the formula for the orbital magnetization has some derivatives like this, but it also has a Hamiltonian in it. So the orbital magnetization is not a geometric quantity in the same sense that the anomalous Hall conductivity is a geometric quantity. Yes?
For this flow wave function, you have usually, I don't know if it's a flow wave for overall system or just some selected bands.
So, the broader context is that this is some two-dimensional parameter, some two-dimensional closed parameter space. So, for example, I could have a magnetic molecule, and as I said before, the x-axis is the displacement of this oxygen, and the y-axis is the displacement of this manganese atom in the molecules. And then I can do little loops in this two-dimensional parameter space, or I can go around some closed space. I need to make it a closed space, so maybe that's not a good example. But the statement is that I can always do this mathematics. I can always define the Berry curvature. I can always insist that if I integrate it over a closed manifold, I get 2 pi times an integer. All of that mathematics may or may not have any physical interpretation. For the specific case where one parameter is kx and the other one is ky, the indices of a Brillouin zone of a two-dimensional insulator, then these quantities acquire some interesting physical interpretation. Namely, the Berry phases are related to components of the polarization, and the Berry curvature integrated over the Brillouin zone, which is the Chern number, is related to the anomalous Hall conductivity. So you can always do it mathematically, but the question is, does it have an interpretation? Yeah?
When you consider calculating a system where you have bands and you have many bands, for calculation, which bands you use?
You have to, for the physical interpretation, to get a physical observable, you have to sum over all of the occupied bands and not over any of the unoccupied bands. So you have to, there's an additional sum there's an additional sum that I have to write here, sum over occupied bands, and then there's a band index on each one of these, so I have to sum over all the occupied bands. Okay. In case some of you may not know what anomalous Hall conductivity is, again, I just want to have a couple of slides of elementary introduction. You know that the ordinary Hall effect, you have some ordinary non-magnetic metal, like copper. You apply a magnetic field in the vertical direction, you pass a current, and you measure the transverse voltage, and after some interpretation, that gives you the transverse conductivity. Of course, I think you know about the quantum Hall effect. Basically, this is usually observed in the context of inversion layers in the gallium arsenide, aluminum gallium arsenide heterostructures, and you apply a magnetic field normal to the layers. You fill some number of Landau levels. Here I had a sketch of perhaps filling 2 Landau levels. The Fermi level is in a gap. So effectively, this system is an insulator because the Fermi level is in a gap, and it's a 2-dimensional system. And so it should have a Chern number, and sure enough, when the system is insulating, so this is a picture as a function of magnetic field strength, the plateaus correspond to situations where the Fermi level is in a gap, and on those plateaus, the Hall conductivity is quantized to E squared over h times an integer. The integer in this case is the number of filled Landau levels. So that's the ordinary, that's the ordinary Hall effect, and then the quantum Hall effect was discovered around 1980. In the case that you have a ferromagnetic sample, you don't need any external magnetic field because the ferromagnetism of the sample itself, it has a spontaneous broken time reversal symmetry. It takes the place of the magnetic field. So even in the absence of any magnetic field, just in the presence of magnetization, you get a transverse conductivity. That's the anomalous Hall conductivity. That's also been known for more than a century because Hall himself also introduced this idea just 2 years later. So that's very ancient. And so you can ask, can we fill in this set of boxes? Can we find a quantum anomalous Hall system? That is to say, it's like the quantum Hall in that there's a non-zero Chern number and a transverse conductivity that's quantized, but in the absence of any external magnetic field. And if we can find such a thing, then it's precisely what I described. It's this quantum anomalous Hall insulator. So there's a place for it sort of in the periodic table of quantum Hall effects, and does it exist? And as I hinted in the introduction, this part of the story was largely started by Haldane, who wrote this beautiful paper in 1988, in which, with an obscure title, about parity anomaly. That's where he was coming from. But from our point of view, what he did is he made a very simple tight binding model of a 2-dimensional graphene-like lattice. The projector is making these a little hard to see. There are first neighbor bonds that are hoppings, and there are second neighbor bonds that have arrows on them. And the reason they have arrows on them is the first neighbor bonds are real, and the second neighbor bonds are complex, and the ones that go in this direction have e to the I phi, and the one that goes in the other direction is e to the minus I phi. Phi and T1 and T2 and delta are parameters in the theory. Delta allows for different site energy. So for example, if delta is not 0, it's more like boron nitride, whereas if delta is equal to 0, it's more like graphene. And what he showed is that this little model is trivially solved, and when you solve it, there are regions of the phase diagram where the Chern number is +1 or -1. Of course, there are also regions of the phase diagram where the Chern number is 0. It sort of depends upon the relative values of the parameters. But basically, what he showed was that at least on pencil and paper, this model is so simple it can be solved analytically. You can show that it is possible to have 2-dimensional insulators whose mathematical properties are such that you have this non-zero Chern number. Okay. I should also emphasize that as you go across this boundary, there's no change in symmetry. So the symmetry of the Hamiltonian here and the symmetry of the Hamiltonian here are exactly the same. if you look at the band structure here and the band structure here, it looks the same. If you can only look at the energies and nothing else, then it all looks there's no way to tell the difference. The only difference has to do with some twisting of the wave function phases that is related to Berry phases in a way that I'll come to in a moment. So as you might have heard other lecturers emphasize, in some sense this topological transition is a new paradigm in condensed matter physics. The usual paradigm is the Landau theory paradigm, where when you go from a paramagnetic to a ferromagnetic or ferroelectric state, there's an order parameter that turns on, and the symmetry here is lower than here. That paradigm doesn't apply here. Instead, what happens when you cross the topological transition is that there's a gap closure that reopens, and then when it reopens, you're in a phase where the electronic wave functions are twisted in some way that's different from what you had before. Okay. So what is it that's different about this Chern number phase relative to the simple phase? So what's the difference, like the analogy between a simple strip of paper and the Moebius strip. So I'm going to tell you what I think is the simplest way to see what the difference is, but it does involve Berry phases. and so here we go. So here again is our two-dimensional insulator. I pick one particular direction, let's say the kx direction, to keep wave vector in that direction is a good quantum number. And then for each value of kx, I calculate this Berry phase in the y direction, and I plot the Berry phases. And what I told you before is that if I average these Berry phases, I get the polarization in the y direction. But I can ask in general, what does this curve has to look like? Well, when I do this at the right side of the Brillouin zone and the left side of the Brillouin zone, those are really the same place because, you know, it's a closed manifold. So I have to have the same value here and here. So the only thing is it can wander around, but it has to come back to itself. Right? Well, yes and no. Okay, so it usually comes back to itself, but you could have a situation where it does this. It maybe winds around a little more than what I've drawn, but in the process of going from the left side to the right side, it goes up by 2 pi. And that's okay because this Berry phase and that Berry phase are really the same thing. In fact, the Berry phase is really only well defined 2 pi by 2 pi. So if I plot it this way, I can think of this curve, and there's another curve here that you can just faintly see, and there's another one, and there's another one. There's this whole family of curves that really all describe the same thing because the Berry phase is really only well defined modulo 2 pi. And so when I come over here, I really do have the same family of values that I had here. It's just in the process of going from the left side to the right side, if I follow it continuously, I go up by 2 pi. And I call that Chern number 1. Is going up by 2 pi. And you can more or less see that now if I have an insulator that has Chern number 0 and another insulator over here, insulator B that has Chern number 1, and I imagine gradually looking at all the Hamiltonians in between and making this plot for all the ones in between, you can't have something that goes smoothly without climbing to something that does climb without having something break down somewhere. And so the only way that those two things, the only way that you can have one go into the other is that at some critical value of the Hamiltonian or some interval of values, the system becomes metallic with a gap closure. So, so this Chern number, of course, it could go up by 2, it could go down by -3. So there's a whole family of values that it could have. And why is this related to the anomalous Hall conductivity? So I guess I've tried to explain why there's this integer topological classification of two-dimensional insulators. Why is it related to the anomalous Hall conductivity? Here's a simple explanation. I told you last time that this Berry phase is really related to a center of the Wannier function positions. So if I look at the wave functions along one of these vertical lines in the Brillouin zone, its Berry phase, I can also think about taking all of the block functions along this line, making a wave packet which is as localized as possible in the y direction, calculating the center of charge of that wave packet, and plotting it here as a position. So now I've got another scale here. The idea is that this distance is one lattice constant along y in real space. And so a change of 2 pi in the very phase is the same as moving a Wannier center by one lattice vector. And so now if I imagine applying an electric field in the x direction, let's say a weak electric field, according to Boltzmann transport theory, you know what that does is it applies a force to every little wave packet, and the wave packets migrate in the x direction, in the kx direction, at a rate of motion in kx, which is proportional to the E field, that's standard Boltzmann transport theory. So as these wave functions migrate, they translate in the y direction, and of course they carry charge as they do that, so you get a current. I write the current as k because it's a planar current. A current in the y direction is proportional to the electric field in the x direction. When the electrons sweep all the way across the Brillouin zone, they move up by exactly one lattice constant. All the electrons shift up, and so you get this transverse current. And if you work out the mathematics of this, sure enough, you get that the transverse conductivity is just E squared over h times the Chern number. So that's the intuitive connection of this funny, very phase, very abstract mathematical concept. Very phase is related to Wannier center position. You drive wave functions across the Brillouin zone. In k space, they move in real space in the transverse direction, and you get a transverse conductivity. Okay. Okay, let me keep going, and then I'll stop for questions a couple more times. There's a concept in topological insulators which is called the bulk boundary correspondence. And the basic idea is this. If I have two topological phases like phase A and phase B, so this one could have Chern number 1, this could be a two-dimensional insulator with Chern number 1, and this could be Chern number 0, this could be bismuth selenide, and this could be silicon, that there should be something funny going on at the boundary. Since we have a general notion that if we imagine continuously changing the Hamiltonian from here to here, that the gap closes at some point, you might expect some funny thing happening like a gap closing, which means like a metallic state at the interface. So the general notion that if you have two topological phases that are different, that something funny has to happen at the boundary. I like to use this example. I learned this from other people who gave introductory talks about topological insulators, so it's not my idea alone, but apparently people drive on different sides of the road in China and in Hong Kong, and people were trying to design a bridge that would handle this case. So, you know, of course, if you drive on one side in Japan and the other side in China, you don't ever have to have a bridge. But if you're close enough, you have a bridge, and then, of course, there are going to be traffic accidents unless you do something. And so this is the design. I don't think this is ever built, but this was the design for the solution of this problem, right? So you have a well-defined topological state A, well-defined topological state B, and then at the boundary between these two things, you have to have some kind of disturbance. And the corresponding statement about topological insulators is that at the boundary, you have some kind of metallic state separating this insulator from that insulator. And in the case of the two-dimensional quantum Hall or quantum anomalous Hall state, what that thing at the boundary is a chiral edge channel. And so what that means is that there's a state at the boundary that has a Fermi velocity in, let's say, the counterclockwise direction, but there is none in the clockwise direction. And that's true both in the quantum Hall state and in this quantum anomalous Hall state. If the Chern number is 1, there's one such edge channel. If the Chern number is -1, it goes the other way. If the Chern number is 2, there are two such edge channels, and so on. So let me try to explain why this is. And the way we usually think about this is to look at the edge band structure. So this is like a surface band structure, but we're still in 2 dimensions. So in 2 dimensions, the edge is a one-dimensional object. So what I'm sketching here is a semi-infinite 2-dimensional crystal, which fills the lower half plane, and then there's a wave vector along the direction parallel to the edge. Of course, this is really a lattice underneath. Because the system is still periodic in that direction, this k is still a good wave vector, so we write it as a wave vector in this direction. and then we plot energies in this direction. These shaded regions are the regions of bulk occupied valence band states and bulk conduction band states. In the bulk, of course, there's another wave vector index in the y direction, ky, and this shaded region corresponds to what energy range you get when you consider all possible values of ky. And then, if there are special surface states at the surface, they may appear like this as states that peek out from the bulk valence bands or from the bulk conduction bands, or you could have some state that crosses from the valence to the conduction band. Now, those of you who have seen band structures probably are first of all thinking, this is a really bizarre band structure because I don't see any left-right symmetry. So why don't I see any left-right symmetry? Well, usually the left-right symmetry is either there because of time reversal symmetry or inversion symmetry. So in this case, we don't have time reversal symmetry because we're always talking about ferromagnetic two-dimensional films. So this is a ferromagnetic insulator. And inversion symmetry is there because inversion symmetry is never a symmetry at a surface because you have vacuum on one side and not the other. So the surface band structure is allowed to have any kind of weird left-right symmetry. And I can count the number of states that cross from the valence band to the conduction band as I move from left to right as I go across here. And that number has to be an integer. And it turns out it's the same as the Chern number we've been talking about all along. And the reason for that, there's a physical connection that goes kind of like this. Suppose I apply a small uniform electric field parallel to the edge of this sample. If there's a non-zero Chern number, then I have this transverse current. I don't know why I called it J instead of K this time, but it's the same thing. It's a transverse current that flows towards the edge. If there were no surface state crossing here, then the edge would be perfectly insulating, and I would be watching charge accumulate at the edge, but it has nowhere to go, and that would be a violation of conservation of charge. In other words, I'm really just asking for the ground state of the system in the presence of a small electric field, and the ground state has to be, by definition, stationary states in quantum mechanics are independent of time, so I can't have a growing charge density, so I would have a contradiction. However, if I have one of these funny edge states that moves in only one direction, then what happens is when the current arrives at the edge, it runs off in this edge channel, and one edge channel is just exactly enough to drain away the excess charge that comes from a Chern number of 1. If you have a Chern number of 2, then you would need 2 edge channels crossing along here in order to drain off the current. So that's the connection. And you can see, the Fermi velocity here is defined as the derivative of the energy with respect to wave vector up to an h bar. So that's to the right. So there's a set of electrons that can move to the right along the edge, but there's no possibility for electrons to move to the left along the edge. And so part of the excitement about topological insulators is that if you can construct a system of this kind physically, it means you have a kind of a quantum wire which runs only to the right and not to the left. And that means that you can't have any scattering. You start putting defects here, and normally what would happen is that an electron hits it and scatters back in the direction it came from. But here there are no channels for electrons to scatter back to the left, and so even if you put defects on here, you just get dissipationless currents that just avoid the defects and run along. So that's part of the excitement of using this for potential applications. Okay, so that's the edge current connection. Conservation of charge tells you that there has to be, these are called chiral edge states because they circulate in only one direction. So the quantum anomalous Hall effect was finally demonstrated in 2013 by the group of Chiken Shui and collaborators. Initially they did it by doping antimony telluride films with chromium to make the films ferromagnetic. And here you can see the transverse conductivity, even at low temperature, 30 millikelvin, was not exactly 0, but the sigma xy was pretty close to E² over h. And since then, they and other groups have improved this Here's an example of vanadium-built films, which seem to do better. And this is as a function of temperature. Sigma xx really does go to 0. Sigma xy goes very close to 1. You have like 1 part in 10 to the 4th, or I think I learned yesterday more like 1 part in 10 to the 6th in the best samples now at very low temperature. But this still only lasts until about until about 1 degree Kelvin. But at least we now have experimental proof that, so this is actually a measurement of the anomalous Hall conductivity as a function of magnetic field. You see that it's a hysteresis loop because at some point the magnetic field flips the magnetization of the two-dimensional ferromagnetic film. And then, of course, the Chern number changes from -1 to 1 and vice versa. Okay, so where are we? What are these useful for? Possible precision measurement, dissipationless wires for microelectronics. There's a magnetoelectric coupling aspect that I won't touch on in this talk. So basically, that's our two-dimensional quantum anomalous Hall insulator. Boy, okay, well, certainly we'll finish this, but I may not do part 2 and part 3, we'll see. So anyway, let me stop here and ask for a moment if there are more questions about everything related to the two-dimensional quantum anomalous Hall case. Yeah?
Can this KY change in the surface state? Because you do the KX, can this KY change?
So what you talk about,
The surface state.
so what I've done here is I've looked at a surface where the unit normal of the surface is in the y-hat direction. In that case, what I'm plotting here is Kx, and then I get this kind of behavior. Now, the crystal might have another face over here, so in real space, there's another face where the unit normal would be in the x direction. On that surface, the ky direction is the good quantum number, so I would repeat this calculation using kx and ky, and now because I'm doing it in a different projection, the projected bulk bands might look a little different, although the gap would be in the same place. And this surface state wouldn't necessarily be here, it might cross someplace else, but what's guaranteed to be true is that the number of up crossings on every surface of the facet is the same, because that number of up crossings is only apparently a property of the surface. It's really a property of the underlying bulk topology, because the Chern number of the underlying bulk topology, which can be determined based on only bulk calculations, requires that the surface, any surface, have the given number of edge channels. So you can repeat this for any different facet. The details will look different, but the number of you could also have, and I'll discuss this later, something that goes up and down and another one that goes up. So you have 2 up crossings and 1 down crossing. That's 1 net up crossing that can happen if and only if the bulk has Chern number 1.
David?
Yeah.
Would a domain wall constitute, would it be a surface state?
Well, if you have a domain wall between a domain of Chern number +1 and a Chern number -1, then yes, that domain wall has to have 2 edge channels, because the number of edge channels is really the difference of the Chern number from one side to the other side. The vacuum always has Chern number 0, so I've always been implicitly assuming that my partner on the other side is the vacuum, which has Chern number 0, but the general statement is if I have material with Chern number C1 and C2, then the boundary has C1 minus 2 edge channels at the edge. Okay, so let me go to the 2D and the 3D. So in 2D, there's a type of topological insulator that's called the quantum spin Hall insulator. And this is a time reversal invariant system, so there's no magnetism here. But we can build it out of this magnetic two-dimensional quantum anomalous Hall state in the following way. We take a system that has spin-up electrons whose band structure is such that those have Chern number +1. And at the moment, there's no, let's say there's no spin orbit coupling, so the spin down electrons are completely independent. And we construct the system such that the spin down electrons have Chern number -1. And then we superimpose these two things into the same two-dimensional material. So within one two-dimensional material, the spin up electrons have Chern number +1, and the spin down electrons have Chern number -1. And so the total Chern number of this system is 0, because to get the total Chern number, I have to add all the occupied bands. So I have one of each. I have 2 occupied bands. Total Chern number is 0. The anomalous Hall conductivity of this system is 0. If I apply a field in this direction, I get no transverse current. But on the other hand, and it has time reversal symmetry. Why does it have time reversal symmetry? Because when I apply time reversal to this system, time reversal does a complex conjugation. So it changes this into -1. That sounds like a violation of time reversal symmetry until you remember that time reversal also changes spin up to spin down. So this +1 becomes that -1, and this -1 becomes this +1. And so time reversal on this system is a symmetry. Right? So it has time reversal symmetry. I actually can show that because it has time reversal symmetry, it always has to have 0 Chern number. One way to see that is if you have time reversal symmetry, you cannot have an anomalous Hall conductivity by symmetry. But it is topological. And it has a topological index, which is called a Z2 invariant. And so if I construct this system in the way that I said, by taking a Chern number +1 and -1, I get a topologically odd quantum spin Hall. This is called the quantum spin Hall state. So I have to explain, first of all, what Z2 is. So what we had before is we had Chern numbers that could be any integer. And in mathematics, the class of integers is Z. So Z runs from minus to plus infinity, running over all integers. Z2 is the set of integers 0 and 1. So Z2 is the name for the group. It's the simplest possible group in group theory, the group that only has 2 elements. It's either 0 and 1 under addition, or equivalently plus and minus under multiplication. That's what Z2 is. So in our new formulation, it turns out, and I'll try to explain why, this index is no longer all possible integers. It's just either 0 or 1. And in particular, if I try to build a quantum spin Hall system by taking a Chern number +2 system and a Chern number -2 system and superimposing them, it turns out that I can adiabatically connect that to a topologically trivial system that I got by using 0 and 0 without a gap closure, but I can never connect it to plus and minus 1 or plus and minus 3. So the classification is just an even and odd classification. And by the way, at some point I wanted to throw in this reference. It's a very nice Reviews of Modern Physics, 2010 by Hassan and Kane, that covers much of what I'm covering here. But in any case, this is sort of the picture of the quantum spin Hall state. And now what happens is, because you have 2 time reversal copies, the ones that were like spin up and spin down, because they're time reversed, get swapped left and right in k-space. Time reversal reverses the sign of k, so you get crossing bands. And so if you look at what the edge channels look like, and we'll see why in a moment, you get a pair of states. So you do have now right moving states and left moving states, but these are time reversal partners. So if this one is spin up, this one is spin down. So you have spin up going one direction, spin down going the other direction. You have these so-called helical edge, helical spin textures on the edge channels. Okay, so let me try to explain why you have a Z2 invariant and not a Z invariant. So to do that, let me just go back and remind you about the quantum anomalous Hall case and the connection with surface states. So on a given surface, you can count the number of up crossings, and I said that's equal to the Chern number. But you can see that the number of up crossings is something that has to be conserved. If I count the number of up crossings, I have excess of 1. I start changing the surface band structure. The net number of up crossings versus down crossings is always 1. It can't change. And that's an integer. If I had a net excess of 3 up crossings, that can't change as I change the surface. And so if I have a bulk system, it has a certain number of up crossings. That's symptom of its underlying topological index. Okay, what about the case where you have time reversal symmetry? So time reversal symmetry now imposes that the band structure has to be left-right symmetric. And if I try to count the number of upcrossings, the net number of upcrossings, of course it's always 0 because of this left-right symmetry. But, so that's always 0. But I can, first of all, I should notice that this crossing in the middle is not gapped. And the reason it's not gapped is because there's a Kramer's degeneracy here. And the reason that there's a Kramer's degeneracy is there's a concept, where did I put it? Well, I'll come to it in a moment. Basically, the idea is that at this wave vector, time reversal symmetry takes the wave vector into minus itself. At the zone center, it is itself, and therefore, time reversal symmetry is a good symmetry at the zone center. And so I have a twofold degeneracy that's enforced here. So these two things that met at the center are guaranteed to cross without any gap opening. That's called the Kramer's degeneracy. Okay, so now the trick is to focus just on one half of the Brillouin zone, since they're mirror images of one another. And what I'm going to do is simply count the number of crossings in the half Brillouin zone and ask whether that number is odd or even. And I can change the total number of crossings. Like, so from going to here, I can imagine making an adiabatic smooth connection from here to here. So the total number of crossings changed from 1 to 3. So we don't have an integer classification anymore. But it changed by an even. So it started odd and it's still odd. And I imagine doing anything else, it will remain so. I also have to point out that there's also a Kramer's degeneracy at the zone edge here. And that's because if you apply time reversal to pi over a, it goes to minus pi over a. But minus pi over a and pi over a are really the same thing because it's on this closed manifold. And so these 2 points in the one-dimensional band structure, 0 and pi over a, are called the time reversal invariant momenta. So momenta means wave vector k, right? So the time reversal invariant k points. But somehow in the topological insulator field, this trim, maybe you've seen trim. So what it means is the places in the Brillouin zone where the wave vector is mapped onto itself by time reversal symmetry. So in one dimension there are 2 of them, and there are Kramer's degeneracy. So whatever band structure occurs here is always glued together at the boundary. And because of that, for example, here this thing falls below the boundary, but because it can never open a gap, I can never get rid of this crossing, I always have an odd number of crossings. On the other hand, I can have another system that always has an even number of crossings. And so there are 2 classes of bulk materials, those for which all of the surfaces have an even number of crossings in the half Brillouin zone. Those are the topologically trivial ones with Z2 index of 0. And then there's another class of materials for which the number of crossings on the boundary is always odd, and those are the topologically non-trivial ones. That's called the quantum spin Hall state, where the Z2 index is 1. Okay, so that's kind of the idea. Again, we can think of it roughly by taking the quantum spin Hall insulator with spin up, adding, so that has 1 up crossing, but now we add the other spin down branch, and if I plot the Berry phases as I go across the Brillouin zone, it turns out there are strong analogies between these plots of the Berry phases and the plots of the band structure, of the surface band structure. So surface band structure, there's an odd or even number of crossings in the half Brillouin zone. It turns out that exactly the same thing happens in the Berry phase plot. If I look at the half Brillouin zone and count the number of crossings, it's either even or odd. So another way of thinking of the quantum spin Hall insulator is that if you have a band structure such that in the half Brillouin zone, the bands zigzag in order to satisfy the Kramer's degeneracies at the 2 time reversal invariant momenta. If it zigzags, that's topologically non-trivial, but if it closes to itself, then it's trivial. So here's an example of a calculation we did on a tight binding model that was proposed by Kane-Millee, where we explicitly calculate these Berry phases as a function of kx for some parameter values. And here you're in the normal state, and these Berry phases reconnect without zigzagging, and in a non-trivial state they zigzag. There are some other ways of describing the topological invariance in quantum spin-Hall states that I find very more obscure than what I've described. There's a Faustian, there are various other ways of doing this. This is the way that I think is kind of somewhat intuitive. You have some notion that this Berry phase is like a charge center of a Wannier function, and so you can kind of see, for example, in this case, if you apply an electric field in this direction, spin down electrons move this way, spin up electrons move this way, so you get a spin current in the quantum spin-Hall system. However, I should mention one thing because it's the big confusion in the field. Although in the quantum anomalous Hall system, the anomalous Hall conductivity is exactly quantized to be an integer multiple times e squared over h, where that integer is the Chern number. In this spin-Hall system, in the presence of spin-orbit coupling, the spin current is not quantized. It may be close to the value that you would expect based on superposing up and down spin systems with opposite Chern number, but because spin is not, so the problem basically is that when a spin comes to the boundary, it can experience a local exchange field which causes it to precess into the opposite direction. So spin density is not a conserved quantity, whereas charge density is a conserved quantity. So there's a subtlety here. So the naming is rather funny. So for the quantum spin-Hall system, you sort of think of it like it's not a classical spin-Hall system, it's a quantum spin-Hall system. For the quantum anomalous Hall, you think anomalous Hall is quantized. So it's a problem in the naming. Okay, so we did the two-dimensional quantum spin-Hall, and I have time to do the three-dimensional topological insulator. And I think I'll stop when I get to the end there, but let me see if there are questions now. Okay, well, let's go on then and do the three-dimensional topological insulators. Here's this two-dimensional system, and I just put some arbitrary crossing thing to measure the, imagine that I have a Fermi level here, I have two crossings, and now I turn this into a two-dimensional system. So now I imagine I have a three-dimensional bulk and a two-dimensional surface, and in the kx direction, if I plot the band structure passing through the center of the Riemann zone along the kx axis, then you get something very similar to what you had in the one-dimensional case. Because along that direction, you basically have a two-dimensional time reversal symmetric bulk, if you like. If I plot in the ky direction, I get something similar. So if I make the plot in the ky direction, I also have bands that behave similarly in the ky direction. So this turns into a Dirac cone type of crossing in the kx-ky plane, and that's what was observed in the ARPAS experiments in bismuth selenide class materials. Here, actually, this little stuff here, this is a little bit of conduction band bulk states that are occupied, so you can see the system is really not an insulator. We would like the Fermi level to be down here, cutting through the Dirac cone. And in more recent work, people have developed much cleaner samples. So basically, the picture is like this. This is a theoretical calculation of what the surface bands look like. This is gamma along some directions in k-space. These are two different directions in the perpendicular plane for some particular surface of bismuth selenide. And you see this Dirac cone, the closure of the Dirac cone is almost in the valence bands, but if you cut somewhere, this is sort of a idealized picture of what the Dirac cone looks like. And then this is the spin helicity part of this story. So again, because these states on opposite sides of this Dirac cone are basically like time reversal partners of one another, it means the spin has to reverse, and it means that when you go around here, the spin has to progress by pi. Incidentally, that means that if you calculate the Berry phase around any one of these loops, it's always pi, because the Berry phase, as you rotate a spinner around 2 pi, is pi. Okay, so how does this come about from the point of view of my picture of the 1A functions? So now what we can do is generalize this construction in which we think in terms of the Brillouin zone in the kx, ky, and kz direction, and we pick one special direction, let's say the kz direction, and we Wannierize, or we calculate Berry phases along the kz, along strings in the kz direction. And so along each one of these strings we can evaluate a Berry phase, or we can think of it as a real space position of a 1A center, and plot that as a function of kx and ky. So these plots are now funny plots. Horizontal directions are kx and ky in reciprocal space. Vertical direction is either Berry phase, if you like, or real space position, where this is one lattice constant in the z direction, and these are the centers of these one-dimensional 1A functions, which are like the charge locations of the electrons in the plotted in the vertical direction. Okay, and what I've plotted here is some time reversal broken topologically normal system. These sheets, it's not drawn very well. These sheets should be just periodic. Oh, I've drawn it in the 1/4 Brillouin zone. So here I had the full two-dimensional Brillouin zone. But just as for the spin Hall case, we went to half Brillouin zone. Here it's convenient to go to a 1/4 Brillouin zone. So 0 to pi and pi, and then 0 pi back to 0, 0. And so these sheets would be periodic as I, smooth and periodic as I go across. And so if there's nothing special happening, that's topologically normal. If I have time reversal symmetry, then I have Dirac cones in this, I call this hybrid Wannier band structure. So this, remember, this is not energy anymore. This is Wannier center position for Berry phase. And so, but nevertheless, the structure is that you have these Dirac cones at the 4 time reversal invariant momenta. In 2 dimensions, there are 4 trim. Each one of these, like this one, when I apply time reversal symmetry, it becomes minus pi 0, which is itself. And so these 4 points are the only 4 points in the 2-dimensional Brillouin zone that have that property. And at those 4 points, we impose, or symmetry imposes, this Kramer's degeneracy, so I get this Dirac cone structure. So in a topologically normal 3-dimensional insulator, the bands would all look something like this, and there might be multiple bands stacked up in the vertical direction, but they all connect to themselves in a non-trivial way. If they start to connect to partners in a non-trivial way, then you start to get some topology. And so here's an example where they connect in a funny way along the ky direction. So in this plane, which is plotting z as a function, real space z as a function of ky, they swap partners, so that's like the quantum spin Hall state, but in the x direction they don't, and that's like the normal state. So it's sort of like topological in one direction and not in the other, and that's known as a weak topological insulator. But then you can have a funny situation like this, in which, let's say, on the left face it's topological, but on the right face it isn't. On the front face it isn't topological, but on the back face it is. And the distinction is really, if I count how many of the Dirac cones are on the opposite side. So I have 2 at the bottom and 2 at the top. 2 is an even number. That's topologically normal as far as the strong index. Okay, so what I'm trying to say is that in this case, there's something called a weak index and something called a strong index. The weak index, actually there are 3 weak indices. It tells you for the kx, ky, and kz directions, does it swap or not. There's a strong index that says count the number of connections at the bottom and the number of connections at the top. Of those 4, if that number is even, if it's 0, 4, 2, 2, or 4, 0, that strong index is normal. But if it's 1 and 3, 3 and 1, then it's topological. So this is the case of the strong topological insulator. And the strong topological insulator is the only one that's guaranteed to have metallic surface states on all surfaces. The weak topological insulator is guaranteed to have metallic states on only some surfaces. So there's a longer story here that I don't have time to go into, but you know, essentially what happens is that the analogy between this picture, which is a picture of Berry phase as a function of kx and ky, and the surface band structure, which is energy as a function of kx and ky. I tried to make that analogy in the two-dimensional case. In the three-dimensional case, it's rather similar. For example, if I did a cut here, I'd find a single loop. I can't cut this with a two-dimensional plane in any way such that I don't get a cut. Whereas in this case, I can pass a plane in such a place that there is no cut. And so that's like in the surface band structure, when I have a strong topological insulator, no matter what surface I look at, if I try to cut the plane across the two-dimensional Brillouin zone, it always cuts through the surface bands and gives me a Dirac cone, a famous Dirac cone. Okay, so let me quickly just put up 2 more slides, and then I'll finish with questions. I've talked about two-dimensional quantum anomalous Hall states, two-dimensional quantum spin Hall states, three-dimensional topological insulators, and that took me 1 hour and 25 minutes. I just want to let you know that the topic is rich with other possibilities. If you could stack these two-dimensional quantum Hall states and make a three-dimensional quantum anomalous Hall insulator, it would have an absolutely enormous anomalous Hall conductivity. It would have very bizarre properties. Basically, every layer has a Chern number of 1, so if you add up 100 layers, it has a Chern number of 100, and when you go to the bulk, it gets kind of enormous. So that would be very interesting. In the time reversal invariant world, I talked about the 2D spin Hall, the 3D weak and strong topological insulators. There's a whole class of what are called topological crystalline insulators. And here the game is a little bit modified of what I told you before. What you do is you say, I have a material that has some particular crystal symmetry. Let's say it has some particular space group. And I define 2 materials that have the same space group to be in the same topological class. If I can get from one with a smooth change of the Hamiltonian to the other, without a gap closure, always staying in that same symmetry group. So always staying in that same space group. And that allows you for every possible space group to do a topological classification for that space group. And the Vishwanath and Bernadette groups have done this in enormous detail in recent years. The best known, those things are called topological crystalline insulators. The best known one is the tin Telluride and related systems. In this case, basically what happens is that there's a two-dimensional subplane in the Brillouin zone where the Chern number is 1 and another one which is 0, and these are mirror planes. And staying within the symmetry group, you can't change that. And you don't need spin-orbit coupling to define the topological crystalline insulators necessarily. There are axion insulators in which the topology, it's basically a special case of a crystalline insulator because the extra symmetry that's being insisted on in this case is inversion. So you have inversion but not time reversal, but these things act a lot like bismuth selenide in certain respects. And then you have semi-metals. So you could have a situation in which the valence and conduction bands do touch at a few discrete points in the Brillouin zone. Those are Weil or Dirac semi-metals. There could be cases where they actually touch along connected loops in the three-dimensional Brillouin zone. And those things also have interesting surface states, Fermi arc states and drumhead states and so on. And then there's topological superconductors. So there's a lot more in the world of topological materials than I talked about. I decided in this talk to make my focus on trying to do this kind of formal connection between Berry phases and Wannier centers and the nature of the twisting of the wave functions that give rise to these topological states. It would really be another presentation by somebody probably better done by somebody with an experimental background to tell you what's really going on in the materials world of these topological materials. But I hope this theoretical, after all, that's my, my expertise, I hope this theoretical tutorial gives you a little better sense, if you were able to hang on to some of it, a little better sense of what the underlying mathematics, how this mathematics of Berry phases and Berry curvatures has percolated into this field of electronic band structure and made this kind of revolution in terms of understanding of topological materials. So I'll stop there and see. We have a few time for a couple more questions.